Hello everyone. In this video, we provide a friendly introduction to MATLAB System Identification Toolbox. What you can see over here is the post I created that nicely summarizes everything that I will explain in this video. Besides explaining this post, I will also explain MATLAB codes that you can see over here. A link to this post is given in the description below. First, we explain the system identification problem. What you can see over here is a transfer function model of a second-order linear time-invariant dynamical system. This is a transfer function. Omega n and zeta, these two parameters, are parameters that characterize the system dynamics. Omega n is a natural frequency and zeta is damping ratio. The goal of system identification is to estimate this transfer function from time series of inputs and outputs that are applied to the real system. When I say to estimate a transfer function, I mean to estimate the transfer function parameters, that is, to estimate this constant over here, the constant multiplying s, and the constant over here. Once you estimate these constants, you can retrieve omega n and zeta. So, if this is our physical system, we can apply inputs, that is time series of inputs. We can apply signals that can look like this. This is time, this is u. And once we shake the system with these inputs, we will observe certain outputs. We will observe time series of outputs. And if this is time and this is the observed output, the output will behave somehow like this. So if this is a random signal, we will probably obtain a random output, filtered a random output. Now, the goal is to use these outputs and the applied inputs to estimate the transfer function. Next, I will explain you how to use the MATLAB's System Identification Toolbox in order to estimate the transfer function. The first step is to define a system. I'm selecting zeta of 0.4, natural frequency of 5. I'm selecting sampling time of 0.01 second. This means that I'm assuming that every 0.01 second I will obtain measurements and the total time for system identification will be 5 seconds. Here I need to construct my system that I want to estimate. So I will construct my transfer function, and here's how the transfer function is defined in MATLAB. I use the tf command. So let us define our system. Okay, so here's our system. Here's our transfer function, and we want to estimate 25, 4, and 25. These are the true values of the parameters that we want to estimate. The next step is to obtain the system identification data. That is, we need to obtain the data that will be used to estimate this transfer function. Here's our time vector. I start from 0, I have a sampling time, and the end is total time. Then I have the initial state, and I define an input signal. So in this particular video, I will use a step response to estimate the system. However, in practice, it's more advisable to use a random signal. For example, you can use here a random noise, or you can use pseudo-random binary signals as inputs. This is because pseudo-random binary signals are known to persistently excite the system dynamics. I'm not going to explain here what is the persistency of excitation. However, roughly speaking, your input signal has to be rich enough to excite all the modes inside of the system. However, in this particular case, the step signal will be perfect, will do the job. Then here I simulate the system. I use the function lsim. I specify the system, I specify the input, time vector, and initial state. Another issue in system identification is that often the initial state of the system is not known a priori. Here I set the initial state to 0, 0 to ease the problem. However, in practice, the system is often not in some initial state, and I'm not going to discuss that, how to estimate the initial state. Here we will just assume it's a 0 initial state, and let's leave it that. Okay, so let's simulate the system and let's plot the results and let's see what happens. Okay, so you need to select the whole screen, you do evaluate section, and here it is. Okay, so what do we see over here? We see basically a typical response of the second order system. I have an overshoot, I have some transient here, and basically I can see the rise time, the settling time, and etc. So this is my system. And this is the output that will be used for system identification. In order to use the system identification toolbox, we need to prepare the data. So we need to create the data structure that collects inputs and outputs. And this function, IDD data, is used for this purpose. So here is the function. You can read the description of this function either like this, or you can open the MATLAB help and you can basically read this function. Creates a data object to encapsulate the input-output data and their properties. Now, what is important here to specify? This is the output of a system, this is the input of the system, and this is the sampling time. There are other options that we will not discuss further. So if I execute this lines of code, I will obtain my input data structure. Now, the function for estimating the transfer function, it's called transfer function est, TFS. In order to use this function, I need to specify the number of poles and the number of zeros in my system. Here, the dynamics has 2 poles. Why? Because this expression or this polynomial in the denominator can be factorized as s plus a term multiplying s plus another term, and these 2 terms are called the poles. That is, I can represent this function as follows: omega n squared divided by what? S plus S1 star and S plus S2 star. And S1 star and S2 stars are called the system poles. What are the zeros? The zeros are the zeros of the factorized polynomial in the numerator. Here I don't have any zeros, so zeros will be basically 0. However, you should be careful here that in practice you don't know a priori what is the correct value for the number of poles and for the number of zeros. This is because you don't know a priori what is the system order, right? If you have a physical system, you have some a priori knowledge about that system. You maybe can, for example, write some models, first principle models, and then on basis of these models, you can say, okay, this is the second order system. However, in practice, this is rarely the case. Often, you don't know the dynamics accurately. So these are the values that we actually assume. And one of the biggest challenge in system identification is to estimate these parameters properly. That is to estimate the number of poles and number of zeros. However, in this case, for illustration purpose, since I know the dynamics, I know that the system has 2 poles and 0 zeros. So I will use the precise values since I want to teach you just how to use the toolbox. I don't want to go more deeper into model order selection methods. For model order selection methods, you can look into the ACAICE and BIC criterion. And if you talk about subspace identification methods, they're more advanced methods for estimating the model order. So let's basically run this and let's estimate our system. So we are using the function TFS. We specify the system identification data structure. We specify number of poles and number of zeros. That is the estimates of number of poles and number of zeros. And let's see what happens. You will get some warning here. I don't want to go into details over here. You can by yourself look later and you can refine this. But for the time being, it's very important to see what's happening. Okay, so here's our model. Let us just retrieve it. Here's our model. You can see that we have a perfect match, that basically our transfer function that's being estimated is perfectly estimated. So this is the estimated transfer function. You can see some other parameters, and this is very important to basically analyze fit to estimation data with 100%. So with 100% accuracy, which never happens in practice, we are able to estimate the system model. And here you see some values of the mean square error. These are the cost functions being used. You get very good match, perfect match almost. Now, another step when you actually estimate the system model is to retrieve model parameters and to retrieve uncertainties. So you can retrieve the model parameters by executing this function, get pvec. And the first value are the model parameters. This is the coefficient in the denominator, numerator, etc. So you have three parameters that are being estimated because it's a function with 0 poles and 0 actually zeros and 2 poles. And you see another term here that this function returns. These are basically some parameters that quantify the uncertainty. And you can read more about that by calling the help of this function, and you will see what is giving you. Get the list of model parameters and their uncertainties. So this is very important. So we call this function with two output arguments, and this function returns the one standard deviation values of the uncertainty in the parameters value. So you get some basically variances and standard deviations of your system identification process. Another step, another very useful thing is to get the covariances of the parameters, which are used for further analysis. They can quantify basically confidence intervals, etc. I'm not going to go into these details. That will be reserved for more advanced video. So you get these covariances. These are very small covariances, basically meaning that your procedure is very accurate. So if you get smaller values here, this means that your procedure was accurate. Okay. Let us now perform the system identification experiment under more realistic conditions. Usually in practice, the data is being corrupted by some form of noise. And let us simulate a noise corrupted output. Okay, so what you can see over here is the output of system that's being corrupted by the noise. So what do? I take the perfect output and I add some random noise, random white noise, right? And I get the output noise. Okay, and let us see now how does my system identification method perform when the data is being corrupted by noise. Let's see what happens. Here again, I formed the data structure, input output sample, and I call the tfast function to get my estimated model. Okay, let's see what happens. We can see now that the values of transfer function, the estimated transfer function, is not perfect, right? We have certain inaccuracies. Instead of 25, that's true value, we get 25.28, right? And we get basically here, instead of basically the value here, that was basically 4, we get 3.97, and here we get 25.31. Now, if you repeat this procedure, under different values of noise, you will get different values, right? So if we again generate the noise, here again I will use another value of the noise, and if I perform the system identification procedure, you can clearly see that the parameters are different, right? Here is 24.96, and before we had, okay, we cannot retrieve that, but you can obviously see that the values are different, right? So every time if you perform a system identification process using different system identification data, using different data or different realization of white noise, you will get basically different values of your transfer function parameters. That is, this is basically an estimator, a stochastic estimator. Your system identification procedure is an estimator, right? What is interesting to observe, if you would repeat this process billions of times, and if you would compute empirical expectation of the parameters over here, for example, you get 24.96, 24, 25, etc. However, if you take all these values and if you average these values, if your system identification procedure is designed correctly, then you should get most likely the expected value or the true value of your system parameters. That means that your estimator is unbiased. Okay. Now, let us see the quality, right, of our estimates. We can clearly see over here that basically you're getting 90% fit, which is excellent. You get these values of the cost functions. This is mean square error, which is relatively small. However, you should get here some relative values, and you also need to perform residual tests. However, I'm going to talk about that in my future video. So let's see the covariances, how they look. Okay, so these are the uncertainties in the parameters that you're getting here. These are the standard deviations. What we can observe, we have a relatively small standard deviation over here, and we have still relatively small standard deviations for these two parameters, but still these are relatively good results, and these are our covariance matrices. We can see here that cross covariances and variances, how they behave, and this is very, very, very important. Now, let us simulate our system. Now, what do? I take the estimated system and I simulate it under the condition of input, step signal, and let's see the results. Okay, so here are our results. This is the noisy step response. The blue line is the noisy step response, and this, let's say, light green line represents basically the simulated or the estimated system response. Of course, on this graph you can also plot the true system behavior, completely unperturbed by noise, and you can compare the, for example, estimated step response with the simulated step response of the perfect system, and you can see how accurate are these results. Here you will obtain very accurate results. So let us now repeat the experiment by increasing the noise, by, let's say, tremendously increasing the noise. Let's say we put here more noise, right? We have a higher noise power. Let's see what happens. Okay, I have a very noisy signal that's not being filtered, right? And I perform my system identification procedure using this noise, and I get only match of 56%, which is still not bad. This is not bad, right? And here should be emphasized that in practice, you will never put a noisy data in your system identification procedure. Here, just for illustration, I'm using the noisy data. However, you will first filter this data. So you will run this data through basically low pass filter or through some notch filter or any type of filter that you design. And then after that, only after that, you will plug in that data in your system identification procedure. Okay, so we can see some values. Let's see the values of the parameters I get. Let's see the covariances. We see much higher basically uncertainties in the system. And let's simulate our system and let's see what happens now. So here's my system response. Here's my noisy data. And then here, for fun, for practice, let's do that. We can also place on this graph, we can put basically on this graph our true system behavior. So what I will do, I will take the data from here, right? And I will basically put it in my function to compare the results. Let's see what happens. And here I will add another line. Here I will just change the line width. This is the third line, 2. And let's say here this will be the exact system response. Let's see what happens if I do that. Okay, so there is an error over here. Actually, I shouldn't do this over here, not in LSIM function. I should do this in my plot function. Let's correct this briefly. So this thing is not going to come here. It's going to come over here. And let's see what happens now. Again, there is an error. Again, of course, when you want to do something quickly, it's never good. So let's see what happens over here once I plot it. Okay, so here we have to obviously to invert the values. At the end, this will be the third time always works, right? First 2 times things do not work, but the third time things start to work. So let's see what happens now. Okay, so we can see basically a more accurate explanation of the system behavior. So the most correct system behavior is of course the system behavior represented by this, let's say, yellow or orange line, right? This is the exact system response. The red line represents the system response, the estimated system response. So you can see the effect of the noise, right? You're still able to get relatively accurate description of the system. There are certain errors, and these errors are due to the noise. Okay, that would be all for today. I hope that you like this video. If you like the videos I make, please subscribe or support my channel. Thank you very much and have a nice day.